Okay, yeah, there's that. Okay, so now I'd like to a little bit of a divergence from the physics and do a little bit of math. We have to do some math, and we need to go back to a part that we skipped that I told you we'd come back to, and that's vector multiplication. And vector multiplication is part of that vector chapter. And I said we'd wait until we need it, and now we need it. So what's vector multiplication? Well, we've got two vectors, and we can actually multiply them, right? Vectors are mathematical quantities, and one vector times another vector equals, well, actually they can equal two things. It can equal a scalar, or it can equal a vector, and those are two different things. You have the scalar product or the vector product when we multiply two vectors. So we're going to talk about multiplication of vectors, and actually today we'll just stick with the scalar product, and we'll wait for the vector product again until we need it, which we will when we get to, I believe, the rotation chapter. But anyway, we're going to talk about the scalar product of two vectors. When you have vector A and you multiply it by vector B, and you get a quantity which is going to be a scalar quantity C. It is one way of multiplying vectors. And actually, we have a different multiplication sign. For the scalar products is a dot, and so it's called a dot product, right? Because sometimes we use dots to signify multiplication. And then sometimes we've got cross products, which is the multiplication sign, right? A cross B equals a vector C, and that's called a cross product. So we've got dot products and cross products. And so today, what I want to do is make sure that we can get through the mathematics of dot products. There's no physics here. There will be physics when we apply it to a physics situation, but we need to do the mathematics of dot products or scalar products, or the multiplication of two vectors that gives us a scalar. I was looking for some images that were representative of what we're doing. I found this calculator with a money bag, and I just had to copy it. I'm not entirely sure what it implies. Does it imply that if you know how to do math, you make money, or is the calculator stealing a bag of money? I'm not entirely sure, and that's completely random. Okay, moving right along. Dot products. So the concept of the scalar products is if you have two vectors. Let's say I have a vector A, and I have a vector B. Let's say vector A points in that direction, and vector B points in, I don't know, that direction. And there's certain lengths. They should be different lengths just to make this as general as possible, make them different lengths. And I want to know what is A times B, what is the scalar product of A times B, A dot B equals what? Well, the concept is that we're going to take the projection of one vector along the other vector and then multiply those two things with each other. What I mean is, let's look at this vector A here, and let's take its projection. What does that mean? A projection, remember, means we're going to drop a perpendicular. So before we did projections when we were looking at components of vectors. So if we want to know a component of vector, we just dropped a perpendicular to the axis, and that's the projection of the vector on the axis. And so the projection of A onto B, right, is that quantity, right, this one was B. The projection of A onto B is that little red vector. That's the projection. It's taking the right triangle and looking at the component along B. So it's just the component of vector A along B. So this is just taking vector components. Let's say that we know the angle between A and B is theta. Then the projection, which I can call, I don't know, A sub B, that's the projection of A along B, just like if it was A sub x. If it was along the x-axis, we call it A sub x. If it was along the y-axis, it would be A sub y. So that's just A sub B. That projection, A sub B, is equal to A times the cosine of theta. That's the magnitude of the projection. And so the scalar product is just the projection of A along B times B, the magnitude of B. That's the scalar product of A dot B. So it's going to be A cosine theta times B. The length of A times the cosine of theta times the length of B. So I've just rewritten this on a new page so that we get, therefore, A dot B, scalar product of A times B, is A cosine theta B. We can just rewrite that as A B cosine theta. The length of A times the length of B times the cosine of the angle between them. So then you may ask, but why did I take the projection of A along B? Why don't I take the projection of B along A? And I can do that, and it's going to give me the exact same thing. Think about it for yourself and see if you can see that I can take the projection of one along the other, multiply the projection of one times the length of the other, and I'm going to get AB cosine theta either way. Let's go ahead and show that. So here I'm taking the projection of B along A. So since the projection of B is longer than A, I just extend A out and then drop the perpendicular down. And the projection of B along A is going to look like this vector here, vector B in the A direction, right? That's B along A. And that B sub A, the projection of B along A, is just the length of B times the cosine of the angle between A and B. So therefore, the projection of B along A, therefore A dot B, which is the projection of one times the other, is equal to A times the projection of B along A, which is equal to A times B cosine theta. Ta-da. Ta-da. A dot B is AB cosine theta. It's the projection of one vector along the other times the length of the other vector. That's scalar multiplication. Scalar product of two vectors, scalar product or dot product.